we've seen this AI trend evolve, I guess, really over the last 1.5 years, I would say, right? Where we've seen projects pop up. And I think it's really in its early phases, though. I think we've yet to see actual applications, right? I think it's more of, if we see some actual thing in production, it's like a MVP, it's a pilot, it's
where Arcium sits in the entire stack, right? Because there is blockchain, which means that a bunch of nodes are running the same software, and that's what essentially blockchain is. Applications are like smart contracts, which are built on top of this blockchain. So what exactly is Arcium? Where does it sit, like, in this hierarchy of architecture? Welcome to the Deco podcast, where we bring you stories from founders and investors in Web3. Before we get started, this is not a financial or legal advice. It's just a conversation about things we find interesting in Web3. Views expressed are our own personal opinions. Deco members or guests appearing on the show may have positions on assets they talk about. All right. First recording of the year. It is 7th of Jan, and I am joined by Yannik, who is the CEO of Arcium. Welcome to the show.
Yeah, thanks for having me, and Happy New Year to everyone listening, I guess.
Yeah, we were just talking about what the cutoff is as far as wishing Happy New Year, but I think 1 week should be fine. So Happy New Year, everyone. Yeah, I mean, let's do away with the part where you introduce yourself, how you ended up here, what is your fascination with privacy and crypto, and then probably talk about some AI stuff. So who are you, Yannik, sir?
Yeah, I'm an encrypted soul. So everything I do circles around privacy and encryption nowadays. That's really the big goal, the end goal. That's the reason why I'm in crypto, is to enable privacy, but not to enable privacy just for privacy's sake, right? Just like people shouldn't enable crypto for crypto's sake. Instead, it should be for some bigger cause. And the bigger cause for me really is building more powerful applications and advancing humanity through that. And so I originally got started with computers and math at an early age, I guess. I think it was when I was 12 years old, and I was playing Minecraft, I guess, and was developing mods for that. And I got started with computer science, so I taught myself at an early age how to program. But then during my decision process, what I should study after school, I opted for law instead of studying math, computer science, or physics, which everyone recommended to me. But for some reason, I decided to, go through with law. But in the process of that, I then at some point, got back to my passion of developing things. So at that point, then I developed an app for iOS devices, so mainly for the iPad, allowing people to use their iPad as a fully fledged working device, which during COVID resonated with a lot of people. And through that, it then became one of the most sold apps in the world. And then just evaluating my two options, continuing with law. At that point, I had my large criminal law course, or building things and seeing hundreds of thousands of people worldwide having better lives, better performance and work, stuff I've been building. I then clearly decided to stop pursuing law and instead going into mathematics and computer science. Yeah, and that's where I met my co-founders, and we had the shared passion for cryptography, mathematics, and we actually met through studying elliptic curves at university. And all of the other co-founders, I guess, have been into crypto longer than I have. And so they convinced me to collectively start building something in crypto that brings privacy, brings encryption. And some people might not realize that, because that's one of the big narratives that I think traditional media has shaped about crypto and Bitcoin and all of that being this anonymous system where everyone's private, which, as it turns out, is not the case, right? Everything is public instead, which has some advantages, but I think in general it's more of a design flaw. I think if you could have a system where you protect privacy, it becomes more powerful to reach more humans and to have more collaborative action and build more powerful systems. And so that's why, we're building this privacy and encryption technology with Arcium.
What was the app called?
Shift screen. So it allowed you to connect your iPad via an HDMI cable to your monitor and then use the monitor as a full second screen, which is something that at that point Apple didn't support natively. And so I was sort of pioneering that. Yeah.
still around? We can play around with it.
It's still around. Yeah, you can still purchase it for $10 at the App Store. There's still people still to this day using it because I think Apple rolled out their own system, but as far as I know, they only support Pro models or something like that. So there's still a lot of active users using it on a day-to-day basis, but I stopped spending any time on that many years ago.
Okay. Like before getting into what Arcium is, like I want to understand what Illusive was, why was this whole revamp? And I think the solution was live and then it was sunset. So walk us through journey till you started Arcium.
Yeah, sure. So we initially started as Elusive back in 22, beginning of 22. And with Elusive, our goal really was to bring on-chain transactional privacy, right? So really at the core of the functionality, I guess, of blockchain, providing means to transact freely with others, right? Have ownership of your assets. But one of the lacking aspects in that regard really has been, and still is actually, a lack of privacy. Because if you think about you transacting to me via PayPal, I don't know your balance, I don't know your income, I don't know what you spend your money on, what kind of websites you spend your money on. And so, which is something you might not want to share, I guess. And so if you do the same thing via blockchain, everybody knows everything, right? And so if we want this technology to go mainstream, we'll have this fundamental problem, not just from I guess, privacy regulation perspective, but also from an adoption perspective, right? Because that's a strictly less powerful system if everything is exposed. And so there has to be a solution for that. And the solution we built back in the day with Elusive was using some advanced cryptography, so-called zero-knowledge proofs, to provide this privacy. And it's actually an incredible concept if you come across it, because you have a blockchain, which is this public ledger of computers worldwide, sending transactions, exchanging information, finding consensus, building blocks on the blockchain, having this transparent information, this transparent state, this transparent information flow. While at the same time, with this cryptography, it becomes possible to interact privately on this public system. So that's what we built with Elusive, and that was strictly focused on the sort of transactional privacy between multiple participants. And one of the big breakthroughs that we designed with Elusive back in the day was decentralized compliance. So decentralized compliance was a way for us to provide this full privacy to users, while at the same time trying to resolve some of the key issues with this perfect mathematical privacy, right? And one problem that comes to mind and has surfaced in the past actually has been a lack of compliance, a lack of accountability. So we designed a system where we said, hey, we want accountability function, but at the same time, we don't want any central trusted party to be ruling over who's a good actor or who's a bad actor. Instead, we wanted it to be sort of algorithmic and private on its own. And that was really this big system that we've been developing. And what we required for that is something more than what we built just for the privacy aspect with Illusive, which was transactional privacy with zero knowledge proofs, which is I have some secrets and I send you some money, you have some secrets, you send me some money, which is always the system of some party having access to secrets. And what we required was not a party to have access to secrets, but basically some supercomputer, some encrypted supercomputer to have access to some secrets in order to be able to check the flow of things and then evaluate who's a bad actor and have some consensus mechanisms, while we can never have any single party have access to that data. That's the big problem. And the way we solved that was through confidential computing. And what confidential computing enables is to operate over so-called shared encrypted state, shared private state. So if you take all of the private information that every human on Earth has, with confidential computing, we, for example, could run some computations over all of that information without exposing any of that information, without having to give that information to, let's say, Google or any other centralized trusted party that executes over that data. And that's the big breakthrough that we've been working on with Elusive. And for that, we use so-called secure multi-party computation, which is another kind of, I guess, advanced cryptography used for these kinds of use cases. And we developed this protocol called Cerberus, and through the process of developing this, just for this, I guess, limited use case of enforcing compliance, we realized the potential of being able to operate in a confidential way over any kind of data, run any kind of functionality, train AI models, infer into AI models, right? Do all of these kinds of advanced tasks beyond just this one single limited task. So that's when we decided to expand our Elusive into Arcio and I guess drop this transactional privacy part and instead build an encrypted supercomputer that allows any kind of computation to be fully confidential. And the goal that we are pursuing now is for everything to be encrypted, while anything can be computed over that encrypted data.
Right. So essentially, Arcium became superset of what Illusive was. Like Illusive is a subset of Arcium.
Good question. Not 100%, I would say. So I think what we did with MPC, I mean, whatever you did with Elusive is something that can be built with Arcium, right? So in that regard, Arcium really is this privacy-wise superset.
Right.
Yeah.
So it can be, but it is probably not the part of the suite right now.
Exactly. So Arcium really is this more of, this generalized encryption machine. Yeah.
Right. So you mentioned AI, and I have to ask. I mean, typically our day at the company starts with looking at Kaito and what is happening in the market and market share and whatnot. And yesterday I saw like 72% of CT's mind share is captured by AI, right? And that is crazy. At the beginning of 2024, I think we were at around 18 to 20% AI. And I think yesterday was probably an all-time high in terms of mind share. And today we have dropped to 56%. But still, more than half of CT's mind share is AI right now. So before we dive into technical stuff of what Arcium does and how it does it, do you get time to spend time on what is happening in the market? If yes, then what are your thoughts with where AI is right now?
Yeah, I think it's interesting because we've seen this AI trend evolve, I guess, really over the last 1.5 years, I would say, right? Where we've seen projects pop up. And I think it's really in its early phases still. I think we've yet to see actual applications, right? I think it's more of if we see some actual thing in production, it's like a MVP, it's a pilot, it's showcasing some single use case, like for example, an AI agent, right? But those AI agents aren't yet used for actual products that find big adoption and reflect this big evolutionary step, I guess, from 0 to 1, I guess, right? We are still in this small scaling aspect. So I think that's why AI will really evolve over this year. I think we will see many more applications and actual use cases pop up.
Like, fine, there are agents and they talk on Twitter and do all kinds of stuff, right? There are agents roasting people and being reply guys to all the main accounts on Twitter and all of that. With all that, we recently published on AI. I mean, we've been writing a lot and we shipped an incredible tool called Sentient.market where it tracks like everything related to AI. But as far as you mentioned about use cases, right? So I feel that like the huge problem with crypto that UX was not friendly and new people cannot interact with crypto. AI can, I mean, in terms of potential solution that will really be helpful, I think AI can take that challenge on, right? And AI agents can act as distribution agents for complicated DeFi applications where users will probably not have to go to Uniswap pools and provide liquidity and go to lend borrow markets and figure out where the best rate is and lend it out. It can be cleaned up in a super simple, clean AI where you just chat.
Yeah, I think one of the aspects here is again security and privacy. I think that many people overlook, right?
Exactly.
So I can just deploy some ChatGPT wrapper on a server, call that financial AI agent, and then people can use that, and that server manages all of balances practically, right? And then at some point it will get hacked, it will get drained, whatever will happen, right? So I think that's one of the big problems that I've also noticed with the recent AI trend, that people seem to entirely forget about big problems that crypto overcomes, and it will pop up again if we aren't cautious about that. And that's why I think what we are building with Arcium is important as well,
Right.
in that regard, because we can solve those issues. We can remove the trust essentially, and I think that's what matters. It's building better UX and removing trust wherever it's possible. And so I think that will be the future, definitely. Being able to interact in such a way, but not having to trust OpenAI or anyone like that.
Anyone, right.
Your assets and the protocols that they access and whatever, are done in a correct way.
So, I mean, as long as numbers go up, we don't care about those things, right? That's the problem. But yeah, I just wanted to mention it because this lays the foundation for, or it lays the case for Arcium. So we will tie it back to how Arcium can help AI in general. But before that, I think we should get back to what it is, how it does, like how it performs computations on encrypted data and so on, right? And tackle like the previous technologies which used to do this and why and how Arcium has improved upon those technologies. So yeah, I mean, it's all yours.
Didn't I just say that Arcium is an encrypted supercomputer? What don't you understand? Yeah. Okay, so basically the start of these kinds of technologies, often called PETs, privacy enhancing technologies, has been trusted execution environments. So trusted execution environments basically are hardware-based security measures. So one example would be Intel, and Intel has a suite of specific processors which they ship with security and privacy promises, right? And so they've been used a lot outside of Web3, and at some point Web3 decided to start using them. We've seen entire networks run on these kinds of trusted chips to provide privacy and security, for example. And one of the big problems that already from a terminological standpoint arise is the trust involved, right? Having to trust some centralized supply chain, having to trust Intel with their supply chain, their attestation chain, all of that they manufacture their chips without backdoors, that they manufacture their chips without ways to hack them, to exfiltrate secrets, right? There can be backdoors by Intel, there can be backdoors by other agencies, by anyone in the pipeline, and there can be backdoors by whoever deploys them or runs them. And out in the field, we've seen a lot of those exploits. I think the last one I saw with AMD is 1 month old, something like that. So every few weeks, we see some new major exploit that has been found, which entirely undermines this trust model. So I view this technology as sort of legacy approach where you just say, yeah, we can outsource security to some trusted hardware manufacturers. What I like to see is really...
So before you go on, like what is happening with this hardware exactly? How is it ensuring that whatever it is, or how is it making sure that there is privacy, basically?
That's an excellent question. So there's cryptography involved, of course. The way you can think of it is that the secrets are being fused into the chips. So you have those computer chips, and then there's some encryption keys and some secrets that are being fused directly into the silicon, I guess. And so within the production plant, there's a mechanism that generates those secrets, which then get fused into those processors. And those keys can then be used to sign and decrypt stuff. And the big difficulty, of course, is you shouldn't be able to decrypt information if you have hardware access, right? So you shouldn't be able to look at the fuses and then decrypt stuff. So that becomes an incredibly almost impossible task to do, but it really works on this hardware level, right? Where you have those production facilities that fuse some secrets into those chips. And so that's really this approach. And if things get compromised, you need to do some remote firmware updates, which then introduces
Other centralized
factors. Yeah, so that's really this clusterfuck, if you will, of potential security flaws, which becomes impossible to manage, I guess. But it provides privacy measures, I guess, for different kinds of applications. So if you're the US Defense Department, for example, and you have some servers within the Pentagon, I think you can use trusted execution environments because you have some guards with machine guns standing in front of them. So I think there's use cases where you can actually use trusted execution environments. It becomes problematic if you want to employ them in this decentralized trustless setting, right? Where you say, okay, I outsource computations to whomever. If there's some centralized actor I have a bilateral contract with, employing a trusted execution environment lowers my trust assumptions. That's nice. But if there's no third party I'm interacting with, it becomes incredibly difficult. And so that's why I feel like there's better answers to this problem, or more nuanced answers. And those more nuanced answers really circle around pure mathematical cryptography.
Mm-hmm. Yeah, I mean, so we talked about TE. What was the next in line in terms of privacy enhancing technologies?
Yeah, so for me, the next step really has been zero knowledge proofs. So as I said, with Elusive back in the day, we were using zero knowledge proofs in order to provide privacy. And zero knowledge proofs allow a party to prove knowledge and the correctness of some statement, basically, without having to reveal the statement, which
But they know the statement, right?
they know the statement, right? So I have a statement. Let's say my statement is, I, for example, know my birth date, right? And so
Right.
with a knowledge proof and some other stuff, I would be able to prove to you that I'm an adult and I'm eligible for purchasing alcohol, for example, right? I could use a zero knowledge proof without having to reveal to you my identity and my exact birth date, right? That's something
Right.
that can be enabled through zero knowledge proof. So with the zero knowledge proof, what I could prove in that context is my birth date, is at some point in time, which then qualifies me to be of eligible age.
Right.
And I also need to provide additional context, which in the blockchain could be some state that is on the blockchain. So you verify the proof, which gives you the truth, and you add the context to it. And then you know, okay, Yannik is actually some person who actually has a valid ID. You get the validity of my ID through some cross-checking with the context, and then I prove to you that I'm of age. So something like that becomes possible with a zero-knowledge proof, but a zero-knowledge proof always has two parties involved. The prover, which in that case would be me, and the verifier, which would be you, or which in the blockchain setting is the blockchain, right? The blockchain simply verifies those mathematical proofs. And so that's zero knowledge proofs, and they've started to be used with Zcash, which
Right.
sort of came quite close after Bitcoin, actually. And Zcash allowed you to have this sort of anonymity and confidentiality when transacting on chain. So it's dedicated blockchain that allowed people to have privacy. And the big problem, however, with using zero knowledge proofs for these kinds of applications always is that it's quite limited.
Right.
It's always one party having a secret and generating a proof over that secret and then sending it to the blockchain or some other party, which can be nice for some use cases, but there's a lot of use cases where I have a secret and you have a secret, and we want to do something together with those secrets without each of us having to generate tons of proofs and interacting with each other, right? And so that's where encrypted shared state evolves, where we want to have shared private state without seeing each other's private state. And that's why I see zero knowledge proofs as this next step in this privacy chain, I guess. And then we come to MPC and FHE, so secure multi-party computation and fully homomorphic encryption.
Before that, I just want to add context. Like the last time I checked Zcash, I think only 15% of the transactions were privacy preserving and rest were 15. Yeah. 85% was public, just as in case of Bitcoin, right? So I don't know whether that is because of the size of the transactions is more, so you require more fees or whatever. But like there is empirical evidence that at least as far as transactions are concerned, zero knowledge proofs have not been adopted. I mean, they probably work, but there is no adoption.
I think it's really for Zcash, and I love Suko, right? I don't know if you know him, the founder of Zcash. I think he's doing great work. But I think one of the limiting factors that hindered Zcash from finding big adoption really has been you as a user just using Zcash for privacy, right? So you're not
There's
doing
nothing else.
right? So I think that's highly problematic. And that's why back in the day with Elusive, we also said, okay, hey, we want to have composable privacy, right? We want to have privacy on Solana and other networks where you can just have some DeFi application and together with the privacy, right? So you don't have to leave your environment where your assets are, your liquidity are, where you feel comfortable with, right? So I don't like this concept of, okay, now I want to have privacy, so I'm going to go to this chain. Now I don't want to have privacy anymore, so I'm going to bridge here.
Privacy is not a product, it's a feature, right?
Exactly.
At least for now.
I think 100% it's a feature and not a product, right? So I think privacy needs to be integrated everywhere, just like if you look, for example, at messaging, right? So you have Signal, which is encrypted messaging, but also within WhatsApp, you have end-to-end encrypted messaging, right? There might be some client-side stuff taking place on your WhatsApp client, I don't know, but at least the channel between the parties, that remains encrypted, right? So I want to be at a point where this encryption is just part of everything and it's not being viewed as something special that a user has to think about, because the user will never think about it, right? And so I think that's one of the big problems. And the cause of that, to some degree, I think is due to the technology. I think the cause of that is due to zero knowledge proofs. I think it's due to building your own network, but you can't blame Zcash for that, I think, because
Of course
those are
not.
one of the earliest players, right? So
course.
I think they're amazing, but I think nowadays going about it and saying, okay, I'm going to bootstrap a new network and that network is not
Not easy.
private, I think that's a bad approach and doesn't seem to actually grow the ecosystem, I think. So that's why I think privacy should be at the fingertips of developers in order to be able to add that to their application without even them having to understand privacy, right? Because down the chain, it becomes more complex to communicate these concepts to people, right? So want to be as early as possible and just integrate it everywhere.
Right. Okay, so we talked about zero knowledge and we had just come to MPC and FHE. So, yeah.
Yeah, so again, encrypted shared state, that's what it's about. So good example, I think.
What do you mean? What do you mean by that?
I think a great example would be in DeFi, an order book, right? It's everyone placing their order in that order book. And that's something that you want. You want to have a private order book, for example, right? Because, I mean, in TradFi markets, 30 to 40% of daily US spot volume, for example, goes through dark pools in TradFi, right? So there's some interest, I guess, from institutional players to have privacy when trading, but I think there's also significant interest from small players to have privacy when trading. And so in order to facilitate something like that, in traditional markets, what you would do is simply add a trusted actor, right? You add JP Morgan and Chase as trusted actor. They create this order book and they match the orders. And unfortunately, they front run the orders, but the front running is less drastic than when it's on the public market, I guess, right? So if you want to do something like this in a decentralized setting, there's no trusted actor. So we need some solution for that. And a encrypted shared state is the solution, where everyone basically says, I have this order, and now I'm going to encrypt this order and send it to the order book. And there's no single party that decrypts everything. Instead, there is confidential computing taking place over that encrypted shared state. Another example of what encrypted shared state is healthcare data.
Okay, hold on. So when I send my order to the exchange and it is encrypted and multiple users like me are sending their orders, what happens then? Like, how is the exchange facilitated?
Yeah, so that's where this black box operation of confidential computing comes in.
Right.
So what happens with both FHE and MPC on a high level, I guess, is the same thing, which is you have some function that should be executed, which is the order matching function, I guess. And then that gets executed over the encrypted state without the state actually being decrypted. And there's no single party doing that, which sounds impossible to do, right? But I can try to explain it on a high level. So the key concept that both MPC and FHE actually use for most MPC applications, it's so-called somewhat homomorphic encryption. For FHE, it's fully homomorphic encryption. Is this kind of homomorphic encryption where you have some data that is encrypted. So the data looks random, right? But the way it's encrypted, it's still possible to operate over that data. So you have encrypted data and you have some defined function, how that encrypted data is changed. So it's being permutated. It remains encrypted, but it's just like you having the plain text data, the public data, the non-encrypted data, and doing those operations, right? So it's basically doing the same thing, but now in an encrypted way, which involves a lot of mathematics, a lot of cryptography. And for fully homomorphic encryption, this process is incredibly expensive and incredibly slow. And MPC is an alternative to this, I guess, to some degree. To another degree, FHE also requires MPC in order to have multiple parties. So let's say you have 100 parties, and those 100 parties all, for example, have a salary. And they want to compute the average of their salaries, but they don't want to share any information besides getting the average at the end, right? Which might communicate some information, but negligible at that size. So all those 100 participants can take each of their salaries, and everyone generates 100 random values. They generate 100 random numbers, each of them. And for a single player, those 100 random values added together should equal to their individual salary. So that's what they're doing. Everyone has to generate 100 random values, all summed together, from your salary. So after each player has done that, generating so-called secret shares, they give each other player one of their shares, right? And keep one to themselves. So at the end, everyone ends up with 100 random values, one from their own salary, I guess, and then one from each other player's salary.
99 from others.
Exactly. So now they just have random values. So what every player then can do is they can add all of those random values together. And at that point, the sum of those values can be brought together, can be divided, and you can get
Average of
the average.
Of the 100. Yes.
Yeah. So that's really the key. Generating secret shares, basically generating random values, distributing it to other players, running local computations, running computations that are communication based, I guess, and then ending up with some public or even encrypted information. And so what's so interesting about secure multi-party computation is that we can operate in different trust models. So there's different security and trust models with MPC. The one that Arcium is operating in is the so-called dishonest majority trust model. So most blockchain networks operate in the so-called honest majority setting, right? Where you require a 2/3 honest majority, for example, right? Or more than half of participants in our blockchain network, more than half of validators need to behave honestly, need to behave according to protocol for the assumptions to hold, right? Which is a big trust assumption to have. You can have the same trust assumption in MPC, but you can also have a trust assumption in MPC called the dishonest majority trust assumption, which means you only require one honest participant. So if you have those 100 participants, and let's say you're operating in honest majority, you would have to trust when sending your secret shares, your random values to all of the others, that more than half
51
your
of them.
colleagues are honest, right? Which with that size might be okay, but let's say you're 10 people. Now at that point, I think it becomes quite problematic. So if you can operate in dishonest majority instead, you only have to trust that there's one honest player, one single honest player, which would be you, right? So
Right.
you're not maliciously collaborating. Otherwise, you wouldn't be afraid of the others maliciously collaborating. So that's what makes this so powerful, right? Because you don't have to trust anymore, because the trust assumption is the smallest one possible. So then allows you to run any kind of computation, not just computing the average of salaries. You can run any computation. You can do confidential training, confidential inference. You can build order books. You can build games. You can do whatever. You can do gambling, I guess, right? You can do everything without having trust involved, and do it in a confidential way, and not require any of those parties then to generate zero knowledge proofs. Because what we can do now is we can say, okay, we have all of those parties in the order book example, for let's say,
Right.
all users in the order book would be those running the computation. That wouldn't make any sense. So we instead say, hey, we take a network which generates those secrets and runs those computations. And what the user does is they just send their encrypted data to the network. So in the past, what you would have been doing in MPC would be that, let's say you have this network of nodes that run those computations. You would give every node a random value. What you can do with Arcium, for example, is you just have your secret, you encrypt it, and you send it to Arcium. And then we have some transformation function, basically, which takes this one encrypted data and turns it into 100 random values with no one seeing all of them, right? Everyone just having one of them. So that then becomes quite powerful. So at the end of the day, how you can think of it is you don't have to be part of the computation if you want to have the average of the salaries. You just take your salary, you encrypt it, you give it to Arcium, and Arcium gives back the average of their salaries. Because Arcium under the hood has this setup where there's a lot of nodes running those secure multi-party computations, and you only have to trust that there's one single honest node within Arcium then.
Like, how is the dishonest majority or single honest actor enforced?
Yeah, so that's a good question. So dishonest majority trust assumption, that's basically an atomic trust assumption, right, that you need to have. So how it's enforced, I guess, is through somewhat homomorphic encryption in that example. So with this example, we would have additively homomorphic secret shares. So you have those 100 random values that are added back together in order to form your secret. If you only have 99 random values, you can't reproduce the secret, right?
Correct.
So you need all of them. You need all of those values. So that's what enforces this dishonest majority trust assumption. If there's one party who's keeping
That is honest.
yeah,
Right.
you're not able to reconstruct. And that makes that incredibly beautiful. Yeah.
Right. Okay, so now I want to understand where Arcium sits in the entire stack, right? Because there is blockchain, which means that a bunch of nodes are running the same software, and that's what essentially blockchain is. Applications are like smart contracts, which are built on top of this blockchain. So, what exactly is Arcium? Where does it sit, like in this hierarchy of architecture?
Yeah, so Arcium, and that's a very conscious decision. And it's crazy the amount of people that also came to us and said, hey, Arcium should be an L1. But Arcium isn't an L1, Arcium isn't an L2, Arcium isn't a blockchain. Arcium is a encrypted supercomputer. And what Arcium being an encrypted supercomputer means is that it sits separately. So there's the nodes within Arcium. Those nodes run those computations, but those nodes don't produce blocks or maintain some Arcium network state. Instead, Arcium can be accessed from existing blockchain networks. So let's say you have a smart contract on Solana, for example, right? And within that smart contract, you have some public functions and you want to have some private functions. Let's say you have some voting smart contract, right? Where you want to allow people to privately vote. When they submit their vote, what happens under the hood is that this smart contract sends a request basically to our network. And our network then runs this computation and settles back the result to the corresponding smart contract. So it feels like to the developer and the user, like you just have this confidentiality within your smart contract. But what actually happens is there's this network that is separate, that processes it and sends it back. So it feels like a co-processor, if you will. It's this encrypted co-processor that sits besides all of blockchain networks. And one other beautiful aspect of this really is that it enables also Web2 users to use that supercomputer, right? Because they don't have to operate on a blockchain. So if you want to have some confidential execution of some functionality, you don't have to say, okay, now I'm going to Arcium and I'm gonna deploy a smart contract, which I think is horrendous user experience. Instead, it's, hey, I have this functionality that should be executed in a confidential way. I'm gonna send the data and I'm gonna receive the final result. Yeah. So that's where Arcium sits. Arcium really sits as this foundational, I would even say foundational internet infrastructure layer, where it goes beyond just blockchain networks and allows any kind of interaction to become encrypted.
So, like, I will reiterate what I understood, and you correct me if I'm wrong. All right. I mean, so let's say there is a swap application like Jupyter, for example, right? And now at the contract level itself, there is a function which, if a user opts into for a privacy based swap, instead of a regular swap, it will branch me out to that swap where Jupyter's probably adds like one or two lines where it tells Arcium, okay, this is the swap that is coming your way. And then the results of the swap will then merged into the regular stuff. Like, is that correct at a high level? It's just a function call as far as Jupyter is concerned.
Exactly. So basically, there's the Arcium smart contract then, and you just call the Arcium smart contract. You basically, when write your smart contract, your own smart contract, you just say, hey, I want this functionality to be confidential. And when you compile it and you upload it, that gets basically split into two parts: your actual smart contract and then the stuff you want to be executed in a confidential way. So every time you call them, it's actually this call under the hood from your smart contract to Arcium, and then it goes back
Result back to you.
Yeah. And we developed a new protocol that adds some very important properties to this as well. You hinted at that earlier, I guess, of accountability and enforcement. So we have a new accountability protocol that allows those computations to basically be guaranteed to be executed, right? So that there's not this case where someone wants to execute an offer and then there's no response from Arcium, but instead there has to be a response from Arcium, basically.
Okay, makes sense. So now I want to understand, like, why is this? You said it's easy to execute for those developers, right? It's not expensive. It doesn't consume as much data for the blockchain, right? So why is it that this is easy versus FHE isn't?
I mean, it isn't easy.
Not easy. I mean,
Yeah, I get what you're saying. So
inexpensive or light is probably
Yeah.
the correct.
yeah, if we want to look at it from a technical perspective. So FHE, fully homomorphic encryption. And
Okay, before that, can you also quantify what is the difference like?
orders of magnitude. So,
Okay.
so basically, if you have FHE, every time you operate in an encrypted setting, you're changing the ways you actually run computations. So by default, we have computer processors, right, that operate in this sort of binary setting, I guess. Within CK, MPC, FHE, you operate over circuits that then mostly operate over fields. And those field values are connected with gates, right? So it's a different setting actually that you're operating in. It's this encrypted setting. So that by default makes operations more expensive, and you, as atomic operations, mostly use additions and multiplications of these kinds of values. And for fully homomorphic encryption, both the additions and multiplications are being executed in a homomorphic way. And what that means is that you have encrypted representation and you run a multiplication or an addition of some of those values. And with MPC, we instead say, hey, we can also use somewhat homomorphic encryption. So we only do the efficient operations in that way, and the extremely expensive operations, which would be multiplication, which FHE has to do this way. We can instead use something called preprocessing and beaver triples, where we basically have some multiplications that have been performed in the past, if you will, and we scale them to the new factors that are being used now. So that's one of the ways that it becomes incredibly more efficient.
Is it something similar to, we had those log tables going back in school where there would be a huge table, like where there would be a base and mantissa, and we would just figure out the log instead of trying to calculate it every time? Sort of table of multiplications that you refer to instead of calculating it every time. That is one. And
Yeah, I think that's an interesting analogy, actually. Yeah. No, I think we can think of that process like similar to that. Yeah. Yeah. Exactly. So that's one
and
of the,
secondly, like multiplication is just addition multiple times, right? Or is that different when it comes to transformations and stuff like that?
it's a bit different because you can't add multiple times because you don't know any of the
Don't know what the numbers are.
Yeah. So
Fair.
that makes it a bit difficult to just perform additions, right? But for this process, we are basically able to just make use of the most efficient aspects of those homomorphisms, which greatly improves the performance, as I said, many orders of magnitude. But the big aspect really of secure multi-party computation is also its flexibility. So its flexibility in regards to being able to have oblivious sorting mechanisms, for example, have oblivious data structures, and to be
You have
able
to explain what oblivious data structures are before you say anything else.
Yeah. So it's basically, let's say you have a large data structure of sensitive information, for example, and you want to use that data structure within your computation. If you go about it naively, if you want to say, hey, I have this data structure and I want to access some element from the data structure. You have a table, basically, right? So you want to access an element in that table. You don't know what element because that information is secret. So it shouldn't be possible to know which element has been accessed. Now, going about it naively, what you would have to do in order for it to be private is to basically access every element, and you would take the index and represent it as so-called one-hot encoding, basically, right? Where it's a lot of zeros and 1 and so you basically multiply every element with a single bit from the one-hot encoding and then sum all of them together. And then you would get the indexed element. But that means you have to access the entire data structure. Which,
Correct.
well, large data structures can be bad, right? So with oblivious data structures, we can access those data structures more efficiently and have them be sorted, for example, without having to go about it this way, which is something that MPC enables. And if we want to build incredibly large order books, for example, or do any kinds of more complex applications, we need things like that. So in that regard, it's very flexible and enables cool stuff. And I guess the coolest thing about it is then building so-called oblivious RAM, oblivious random access memory, because what down the line I want to enable with Arcium is for any kind of computer program to be executed in a confidential way. So going far beyond what your smart contract execution, I guess, enables, where it's sort of this limited scope, right, of runtime, but instead saying, hey, I want this confidential computation to run forever. Something like that, right? Where it's an actual state machine within this encrypted environment, which would require, for example, having RAM and heap be encrypted and to be accessed. But that might take a while to
Okay.
come to reality. Now, there's also other important aspects, which are, let's say you have this encrypted order book, or let's say you have a game, right? And you play this game using confidential computing. So there's some fog of war mechanic, right? There's a trustless game you can play on the blockchain. But at the end, you want to have a public result where it's public who won the game, which means at some point you need to access this encrypted information. You need to exit from the encrypted representation and decrypt something. And that's something that's possible with MPC because we have those players, and those players then can, if the rules of the computation say reveal the result, they can reveal the result. So they can reveal who won the game at the end. So that becomes possible. So so-called selective disclosure is possible. So we can freely move between encrypted and public representation of data depending on the application. And that makes it quite powerful because then it becomes this sort of composable technology that can be used on public blockchains where you have public information and private information, and you can switch between all of those without having to go to some different network and bridge your assets every time, I guess, right? So it all happens within a smart contract, maybe, where you can switch freely between those representations.
Okay. So from what I understood, again, correct me if I'm wrong. So with FHE, the solution becomes extremely bulky, and with somewhat homomorphic encryption, what you have done is shed a significant amount of weight off of that, which allows you to be light and scalable, but which is more than enough for the use cases that we are talking about. Is that fair?
Yeah, exactly. I mean, that's entirely true, yeah.
Okay. And Arcium is a network in itself, right? Although it's not a chain or it's not an L1 or an L2, but it is a network nonetheless. So, and I'm assuming that when it is in its final form, it is going to be a decentralized network because, again, I mean, you can't afford to have 2 or 3 parties which are doing any of this. So, how are participants incentivized, and like, how does all of that work?
Yeah, so Arcium on its own really should be a fully autonomous network, right? So, I mean, the way I think about it really is anyone being able to become a node within Arcium, also becoming a specialized node within Arcium, right? So, the design of our network also doesn't force participants, for example, to come with specific hardware requirements. Instead, it's really the system where you can provide confidential computing power. And within Arcium, we have different protocols. So you can provide confidential computing power even for different protocols. So let's say if your hardware are some GPUs, you're mainly focusing on our Manticore protocol for processing confidential ML operations, for example, right? Whereas some other node really is only focusing on some confidential DeFi applications. So that's one key aspect. Now, Arcium on its own functions with a staking and slashing mechanism. So the way we are able to add staking and slashing to a network which isn't a blockchain,
Right.
which is questionable, right, is by having smart contracts on existing blockchains. So if we take Solana, for example, there's this Arcium smart contract on Solana that is used for this coordination of the confidential computations that come from Solana smart contracts and are being executed by the Arcium network. So it's really this gate through which the computations pass and the callbacks are being sent back. Now, if there's a case where, for example, a computation fails, no output is being produced, someone has to be punished. And there's where the staking and slashing mechanism comes into play. And that's what I mentioned earlier with this accountability protocol, so-called cheater identification protocol, an identifiable abort, which allows to cryptographically identify any kind of misbehavior and then punish the misbehaving node, which then turns Arcium into this autonomous, confidential execution engine, right? Where you really have an encrypted supercomputer, because when you send something in, something will come back. If not, whoever caused nothing to come back will automatically get punished. And that's what makes this so beautiful, right? That's why it really becomes this foundational infrastructure layer. You don't have to go for some trusted entity. There isn't some trusted player involved. Instead, it's really, I'm sending something in, something comes back. If not, whoever caused it will definitely get punished for this. I think that's really the core setup, and that's how Arcium functions. Yeah.
Right. So now getting back to AI to close that loop, there are two questions on my mind essentially, right? I mean, one is like all these agents are now, for example, AI XPT tweets about different assets and what is interesting going on about those assets, right? So probably there is some logic as to how it picks that asset and what part of that asset, whether it is volumes or something fundamental or whatever, that it chooses to highlight, right? Like a few people maybe understand how AI XPT essentially arrived at that particular asset. But if we take a case of Zerebro or something like Truth Terminal, they are tweeting things that are seemingly random. And if we are to have like AIs as a part of critical functions, then there has to be a way for us to understand how they arrived at those particular decisions, right? I mean, I'm assuming that they traverse through tremendous amount of trees where one road just branches into multiple, and then at each decision point you are making some sort of a decision to arrive at a conclusion that the AI has arrived. So that is point number one that probably don't understand to the full extent as of now. And second is what you mentioned, right? I mean, if let's say you use ChatGPT to create some sort of an application where AI is executing trades on users' behalf, and there is a backdoor and someone exploits that, then it's all over for anyone who's using that. So, in this scheme of things, like does Arcium fit into any of it, or how does it do it?
Yeah, so there's actually a lot of aspects where Arcium can address critical flaws. So the first aspect really is, how can I trust AI agent, right? There's some Twitter account tweeting something, and it's presumably an AI agent, right? But
Right.
there's no way of knowing. So some of those AI agents are just being executed on some central servers. They actually are just ChatGPT wrappers. Some of them, to some degree, use trusted execution environments. The big problem with trusted execution environments are what I mentioned earlier, plus things like what many people don't consider. Even if you were to build some AI agent with a trusted execution environment to execute all of the logic, there's signing keys for the enclave that's being executed within which the agent lives. So whoever has those signing keys can just do whatever, besides who has access to the TE, most likely can also exfiltrate things and manipulate things. So there's just this immense number of attack vectors, which makes me dislike the setup. Instead, I want it to be trustless and autonomous. And that's what, as I said earlier, we can do with Arcium. We have this staking and slashing mechanism. We can have some autonomous execution environment. And this autonomous execution environment can maintain secrets. So it can hold assets, for example. It can perform actions. It can have some encrypted secret knowledge, right, that builds up over time. I think that's an important aspect. Being able to actually know, okay, whatever someone tweeted came from this environment. It's this cryptographic environment which sends some transaction on chain, signs something, relayers send that signed message to Twitter, and it was tweeted. And we know that the API keys are being securely stored within that environment because that environment signs them and generated those keys originally. So I think that's an important aspect already, removing the trust, because we now know, hey, everything happens in this cryptographic environment. Another aspect is understanding the decision-making process. So I think one aspect to that is, and I would classify all of that as responsible AI, I would say. So there's responsible AI, and I think the subclasses or categories would be privacy, for one, if we say responsibility against humans, I guess, but also explainability, understandability, right? Being able to understand the decision-making process, being able to understand what inputs led to a decision, to what degree different inputs led to a decision-making process. So we published a paper about explainable privacy-preserving AI, which combines both, which allows you to, let's say, have private data and have a private model in which you run some computations. So you don't know the model, you don't know the data. I mean, you know the data, I guess, but you know the effect that your data had in this inference process, which gives you explainability without revealing all of the details of the model, right? So I think it's an important or an interesting concept to say we have encrypted models. So we have an AI agent that runs whatever function. We don't know the model because I guess the whole stick of that AI agent might be that it has some proprietary logic, right? So you want to use that agent for trading, for example, because it claims to have the superior model. And then we say, okay, we don't need to know the model, but we want to be sure that this model is actually what is being used. So verifiability, public auditability, basically, where we want to say, hey, I want to be certain that this logic is being applied to everyone using this model and I'm not getting ripped, right? So the model can remain encrypted if it's in an MPC environment, and inference can be executed, and we don't need to trust that someone switched the models, for example. That's something that's possible. And explainability we can add to the equation as well. Yeah, and I think in regards to AI agents, there's so much more that people don't even think about. Let's say you have multiple agents, so you have some agent swarm, I guess, and those agents could then, in a confidential way, collaborate with each other, right? So we can have confidential, trustless collaboration between those agents where they exchange information and coordinate. And again, I think in order to actually unlock the value of those agents, we have to deploy them in such a setting, because otherwise we will never be able to give them sensitive information, give them access to assets if they can do whatever it can run in some guy's computer in their basement.
Yeah, that makes sense. In terms of the privacy models, right? You said that because the models will have to be proprietary.
I mean, they wouldn't have to be, but they can, right? So you can have a setup where it's a public model, but I'm saying you can also have end-to-end encrypted AI, right? Where you have sensitive data that is being used to train a model using Arcium, for example. And then you don't even reveal that model. You keep that model encrypted and now say, okay, this is now powering an agent that people can use. And whoever uses that agent for whatever functionality, they're going to have to pay some fee, and that fee gets redistributed to the people providing the sensitive data that's being used for training. So we can have some feedback loop, I guess. And on top of that, when you use the model, you don't provide a public data, you provide a private data. So that would be end-to-end encrypted AI. And any of those privacy aspects, right? Training, actual model weights, right? And inference can be private or can be public, I guess. All of that is possible, but it's possible to have the whole suite be fully encrypted.
Okay. And like in terms of like the market, right? Like, is there a 2x2 matrix, like classic matrix, where Arcium lies and where the rest of the solution, or you can just talk to what the competition currently looks like, privacy preserving technologies?
Yeah, I think it's amazing that I've really seen an uptick in projects in the space. The space has really been growing over the last few years, and especially within the last 6 months or something like that. I think I've really seen a lot of more developers going into that space. And yeah, as we discussed in broad detail, there's different kinds of technologies. I think all of those technologies at the end of the day have their role in providing privacy, right? I think the answer is combining technologies for different use cases. Technologies fit better for individual use cases. And yeah, I think we're reaching right now a point of maturity where it becomes actually possible to use this technology in real life applications. Because I feel like what has been done with CK in the past has sort of disillusionized people, I would say. Where it was this, hey, with CK, we have now some CK chains where you can now have private applications, which simply wasn't possible to do because you didn't have this encrypted shared state. So there's now this notion, this understanding that encrypted shared state is what matters, and there's different technologies to operate over that encrypted shared state. So I think that really has been amazing. And the privacy space, I guess, as a whole is still very, very early, I guess, and relatively small. But I think what we're addressing really is the entire market of Web3 and beyond that. I think that's an important aspect to realize. I think what we're doing is we are bringing Web2 use cases into Web3 because institutional players can now access this new financial infrastructure because they can now remain private and remain compliant when doing so. Or we can have new coordination, and we can have the most traditional players, let's say defense players, right, use this kind of confidential computing. Maybe not storing data on a public ledger, I guess, but using this kind of distributed confidential computing that requires no trust assumptions to coordinate. I think that's what makes this so exciting, because it really makes it more tangible and allows for many new players to come into this world.
What do you think are the top 2 or 3 use cases of Arcium whenever it goes live?
The top 2 or 3 use cases. I think for me personally, AI is one of the biggest use cases, simply because I think in order for AI to become more powerful and in order for it to benefit humanity and become more valuable, we need some responsibility and accountability mechanisms. And with privacy and autonomous execution, we can do that. We can make it more powerful, make it more accessible, have a bigger user base. And
So Arcium is like AI infra, is a part of AI infrastructure.
yeah, I think AI infrastructure is a subset of what Arcium does. So at the same time, I'm incredibly passionate about DeFi, confidential DeFi, right? Being able to have financial freedom. I mean, that's on the individual level, right? So if I was to go into a political mission, I would say, hey, now it's possible to have financial freedom, true freedom, right? Because you can own your asset and you can own your data. Now, what's also important in that regard, as I said, bringing on institutional players, right? So being able to actually make this more efficient, more trustless, composable financial infrastructure accessible to more players. So I think that's why AI and DeFi are so interesting. I think healthcare, for example, I mostly would classify nowadays not as a distinct use case, but instead as something that plays into AI. I think the future of healthcare is AI. So I think for healthcare to utilize AI, it will require privacy. So I think private AI is something that superset of healthcare, I guess. And the third use case in Web3, if we limit ourselves to Web3, I would say is DePIN. I think DePIN will also greatly benefit from being able to have confidential autonomous execution without requiring any trusted players, being able to, for example, aggregate and distribute data without requiring some company to do so.
And I mean, I'm sorry, I'm going back to scale because you said, so let's say when Arcium goes live, it would be like, is it possible for all Solana's transaction to be routed through Arcium?
No, because that would, I mean, if we strictly say all of Solana's transactions, that would become difficult.
Essentially, what I'm asking for is like 1500, 12 to 1500 transactions per second, I guess, right?
I mean, so the thing with Arcium is that basically scalability wise, there's no limit of how many transactions Arcium can process, because computations are being processed in computational clusters, and you can just have an infinite number of clusters in parallel, I guess. And at that point, the bottleneck would actually be Solana, because we do orchestration via this smart contract, right? So
Right.
I think at some point that would become the bottleneck actually for confidential computations. What I would say certainly is what we're aiming for is that every Solana smart contract will use confidentiality, and at some point, I guess also other networks, right, will within their smart contracts use Arcium for confidential computing. So I think what we've seen is that almost every developer, almost every application has use cases for confidentiality, and being able to just access it as a native functionality, I guess, at the end of the day, right, makes it way more powerful and accessible.
Okay, that's fair. And what do you see as one either technical or market related challenge for Arcium, and how long before it's launched?
So we're in private testnet right now, and people are building applications with Arcium. Mainnet launch, I can't give you a fixed date.
Okay.
That will still take a bit, I guess. There's some more stuff I want to add to Arcium before going into mainnet. I think one of the things really is, as I mentioned earlier, we have multiple protocols, right? So we have Cerberus, this protocol that we've developed over the last few years. And end of last year, we acquired our largest Web2 competitor, who've been building out Manticore over more than 8 years, which is a MPC protocol for private AI. And so right now, it's basically us also merging that together, right? So I think I wouldn't really call it a technological challenge, because it's more of a just time and engineering.
Logistics. Yeah.
That's what I would call it. But then at that point, we'll be able to offer Arcium as this generalized confidential computing network, which under the hood has multiple protocols and tailor fit, I guess, for each use case, right? Or not even use case, but functionality within a computation, right? Being able to switch protocol representations and then move between those to be as efficient as possible. Yeah. And besides that, I guess we are always striving for being as efficient as possible, right? So I think there's so many more optimizations we can do that we are working on the hardware level, on the network level, on the speed of light level. So there's so much stuff going on now.
All right. This was great. Thanks a lot for spending time.
Yeah, thanks for having me. It was a pleasure.